looking at some details about a collision. And this is a big part of this lecture is collisions. And as we get further into the semester, you're going to see that there's going to be a collision that occurs that's fairly, you'll see collisions are kind of out there when you start talking about quantum particles. But without going into any more details than that, what I want to do is I want to show you my review of what we did last time. So ultimately, we want to talk about momentum. And we said that when I look at mechanics, the two things that we're going to focus on in mechanics is conservation of momentum and conservation of energy. And the principle of relativity says that momentum and energy, conservation of energy and momentum cannot be violated. It guarantees that the laws of physics are the same no matter what. So if they're the same in mechanics, they got to be the same in relativity. So what we're doing differently here, though, is that we agree that these guys are going to be okay. But the problem is that we have to live with the idea that we have to modify momentum and energy. So what I'm doing now is I'm showing you that we're going to have to modify our definition of momentum. Not the conservation law of momentum, but the individual momentum. And I know that some of you SOBs are probably thinking like, well, if you're changing momentum, then you're sort of like changing momentum to make sure that conservation of linear momentum is okay. And I'm going like, well, the principle of relativity tells us that the laws are the same for all frames of reference. So if I go into a frame and I know by the principle of relativity that these laws must be the same, so maybe I just started with an incorrect version of momentum to begin with. And as we get to these more, wild regions of imagination, like moving close to the speed of light, that maybe our momentum definition wasn't correct to begin with. And that turns out to be the case. And by the way, we're going to do the same thing with momentum when we get to quantum mechanics. It just means that at this energy level, we have an incomplete description of momentum. But for low energies, the momentum that we see, the classical momentum, is correct. It's just that now we're getting to extreme situations. So this is the whole reason why I'm doing this. And so what I said here is that we started with case number 1. And we looked at a one-dimensional collision in the S frame. What do I mean by the S frame? I have a little red observer in the S frame. He's at rest at the center of mass of this collision. And so what we imagine here is that we have a red and blue particle coming in, which we talked about before. I defined the velocity in the X direction to always be not the velocity, the speed, and the speed in the Y direction to be B. So depending on which quadrant we're in, I'm going to call up as positive, down as negative, as you would expect. And so when I start to look at this picture here, what you're seeing here is that the before and after tells us that I have a particle coming in initially in the B direction, none in the Y and the X. And then afterwards, it comes what? It comes in the negative B direction. And then I look at the same thing with the particle 2. It's moving downwards in the negative B direction. And then it comes back up in the positive B direction. So when I look at the total momentum of the system, I then add the velocity component since the mass is the same for both of them. And I get that the momentum before and afterwards are exactly the same. Momentum is conserved. What a shock, right? You spent all of physics 4A figuring out some of this stuff. And then all I did here is I go from a one-dimensional collision to a two-dimensional collision. So now in this two-dimensional collision here, I again have my observer in the center of mass frame. And so what you're looking at here is that All I did was change this one to have X components and Y components. So this situation should be no different, but I'm trying to set you up for the more complicated situation. So now you could see here, I have the initial momentum of 1 and 2. You could see that 1 is moving into the first quadrant, so I should have velocities that are positive A, positive B. When I look at momentum 2, it's moving into the third quadrant, so I should have what? Negative velocity, negative velocity. So then afterwards, this guy's going down. If it's going down, I should have A, and then you could see that the Y component is negative, so it's in the fourth quadrant. This guy's in the second quadrant, so it switches signs. So when I add the momentums for beforehand, you could see that I got to add A minus A for the X components, B minus B for the Y component, and when I look at the total momentum beforehand, it's 0, which is exactly what you should have expected from this case here. It's exactly the same thing. It's just that now I have a two-dimensional direction, and then afterwards, with the same type of reasoning, I get 0 momentum before and after for the total momentum, that is, and so therefore, again, momentum is conserved. Why did I do this? To jump to this guy now. When we're looking at the same two-dimensional collision, I now have an S prime observer. This S prime observer is this chick here with the green skirt. And what you're seeing here is that she is moving in the X direction along with ball number 1. So according to her, she is at rest and everything else is moving. And when I look at this thing here, this implies here that the momentum of ball 1 is then just going up and down, because that's all she can observe in that prime frame of reference. And ball 2 still comes in and goes out, but then we did a physical interpretation of what happens here, and what we find is that the momentum has to go to twice the value. But we can do the same type of analysis with a Galilean velocity boost. So if I do that, I do this boost here, and note that this is only in the X direction where she's moving. And so what you're seeing here is that if I do this boost in the X direction, the B is not, the B's will not be affected because that's in the Y direction. Only the X's are affected. So in the X direction, because she's moving with the ball, I get A minus A, which gives me 0, which is exactly what this picture implies. And since the B's are not affected because she's not moving in the Y direction, then the B's are left alone. So you could see the momentum with the Galilean boost literally goes up and down. But now, if I go into the ball 2 frame of reference, look what happens. Ball 2 is already moving in the negative A direction. So when I do the Galilean transformation, I get minus A and minus A, which then gives me minus 2A, which is exactly what we physically observed, last lecture. And then the B's again don't change, so it continues to go in the negative B direction. So if I apply this kind of thinking, what you're going to see here is that then I could go from this picture and I could go to my table. So here I go. From this picture, you could see I'm going, what? In the positive B direction only. Afterwards, it's got to be going in the negative B direction. So now that we know we got that minus 2, that 2 factor, then I look at this guy here. It's got to be going what? Into the third quadrant with minus 2A. And then the B component is still minus B. Afterwards, it continues in the negative direction, which is minus 2A, but now the B component tells me it's got to be in the positive direction, which is this. So when I look at the total momentum, In this case, you're seeing that the total momentum is not zero, but it's minus 2a and 0 for the momentum. And then afterwards, it's the exact same thing. Again, shouldn't be a surprise. Galilean relativity applies to classical physics. Classical, momentum tells us that that must be the case. But there's one small problem here. We know, right? We have a problem. We know Galilean boosts do not transform in space-time, right? They don't give us the right transformations in space-time. This implies that we must use Lorentz boosts. And this is where the problem lies, right here. And so what we got to do here is that when I think about this, I'm going to go from the S to the S prime frame. And what that means here is that if I do a Lorentz boost from what we've talked about here, I'm then going to have this type of scenario, right? It's a Galilean transformation, but now I have this denominator here. And what really complicates things is the y component. So when you look at the y component, there is a denominator which is very, very different in the Galilean transformation, which then becomes gamma 1 minus v, ux c squared u of y here. And ultimately, the reason why the Galilean transformation really fails is because of this term right here. You're going to see that this causes Galilean boosts to fail with momentum conservation. And it's because when you look at the y component, there's a mixture of y and x. And so what you find here is that I need to do these transformations here. So now what I want to do here is that I want to redo case number 3 with a Lorentz boost here. And I'm going to have to do a couple of Lorentz boosts. And the reason why I got to do a couple of them is because this time I have velocities that are going to be moving in the positive direction and the negative direction. So I have to apply it in those cases here. So let's focus on ball number 1. What do we know about ball number 1? Well, when you look at ball number 1, we saw that what we end up doing here is that we have components like this here. So if we come back and we look at the components, the only component that matters is this guy right here. So and then you could see that afterwards I have that component. So it's really the only thing that's going to change here has to be what? The denominator of the y component. So when I look at the ball number 1, I'm going to get what? I got to go from 0 to b, and then I got to go from 0 to minus b. And what you're going to see here is that now I have my boost here. So when I look at my boost, what you're seeing here is that I got to get what? I'm going to get 0 You know what? Maybe I should step back a little bit before I do this. Let me look at this a little bit more carefully here. What do I know about the observer? I know that the observer moves with Vx equal to A. But what is the motion of the ball to begin with? The motion of the ball is also A. So what this implies here is that when I write V times U of X, that's got to be A squared. And so then I'm going to write my beta in this case as A over C. Okay? So now let's go look at this thing here. So if I look at ball number 1, we have these two states right here. So what do I mean by that? So if I go from 0 to B, and then I do my Lorentz boost here, my 0 still stays the same. Why does it stay the same? Look at the picture. There's no X component. And so it's only the Y component that changes. So then I'm going to get gamma of 1 minus beta squared over B. And then if I look at, obviously, if I'm looking at this guy here, and I do the exact same thing, I'm going to get 0 of gamma 1 minus B squared of minus B. Okay, so now I got both of my components here. But now let's go look at ball number 2 here. So if I look at ball number 2, one of the things that we saw here is that this ball is doing what? This ball moves in the negative direction.
Carlos,
Yes.
what do you mean up there in the red? It causes Galilean boost to fill with momentum. What did you mean to say Lorentz? Or I'm lost there.
No. Galilean.
Galilean?
Because what I showed up here, in this case, the Galilean boost conserved linear momentum. So if I boost into her frame, which is different than the center of mass frame, what you're finding here is that this thing changes. I mean, there's no problem here. The momentum before and afterwards is exactly the same. I'm just telling you that there's a problem. The problem is we can't use Galilean transformations, right? We can't use Galilean transformations. We have to use Lorentz boost in order to, apply relativity. But what's the problem? When you look ahead, you're going to see that where the problem that causes Galilean relativity to die is because you get the mixing of what?
Space-time? No.
Y and X components. It's the mixing of these X and Y components in the velocity transformation that will cause the problem. So this is sort of like I'm telling you ahead of time where the problem is at. And that's where that's at. Because you're going to see that the algebra gets really intense. And I'm not even going to do the algebra. I'll let you do the algebra. I show you in my notes how to do it, but the algebra is pretty intense. So now, if I look at ball 2, we could see here that it's moving in the negative direction. So if it moves in the negative direction, this implies here that our Vx now is minus A instead of plus A. We have that negative sign that we had to contend with. So what this tells me here is that when I look at the quantity, 1 minus Vux over C squared, you're going to see that this guy's got to go to 1 plus beta squared. And that's where this minus sign turns that into a plus sign. So when I look at that detail, then here I go. I know that the ball started with what? So if I look at ball 2, we started with 2a and minus b. And then we started with minus 2a and plus b. So if I look at the x transformations, what am I going to get? Okay, right? These are my Lorentz boosts here. When I look at that boost, I'm going to get, for the x's, it transforms like that. For the y's, I'm going to get the gamma of 1 plus beta squared and minus b. Okay, that's where that plus beta is coming from. And then if I do it for the, now it goes upwards in the y direction, so then I still keep the same x's, but my y now becomes plus b. So then if I go and I summarize this thing, I'll summarize it in the table as I did before here. So that means here, I'm going to have my u1. If I look at my u1, I have 0, and then I get gamma 1 minus beta squared b. And then afterwards, I get the exact same thing. Okay, that's my first one here. So then if I do my second one, they're more complicated, as you can see here. I'm going to get this 1 plus beta squared over minus 2a, and then I'm going to get this gamma 1 plus beta squared over minus b, and then I do the exact same thing as up here. And so here's what we have now. This is the before, this is the after now. And so when you're looking at this thing, what am I seeing here? So now I'm going to look at the total momentum here. And which total momentum I'm looking at? I'm looking at it from the prime frame again. And this will have units of Newton second. The algebra is intense. Okay? It's pretty intense. And what you're going to find here is that I do get a total momentum initially in the prime frame. I do get a total momentum afterwards in the prime frame. And what you're going to see here is that when you do the algebra, and let me tell you, the algebra is intense, really intense. This is what you're going to find. That the total momentum before is not equal to the total momentum afterwards. That means that, so if I was to really look at this thing, right? So I'm saying that you got to do the algebra. And, you know, I actually have it. Let me see. I think I have my notes up right now. When you look at my notes, let me set this up so that you can see here. What you'll find here is that you get this. That when you do, this is what the total momentum looks like beforehand. This is the total momentum afterwards. And what you find here is that the difference is in the y components, not the x components. And you could see it may seem like a little bit, just because there's a minus difference between these two. And you might say, well, God, that's really only off by a minus sign. Maybe you did the algebra wrong. Nope. There's no mistake with the algebra. But what you find here is that those two momentums are different. In other words, they do not follow a Lorentz boost transformation. So in the end, what does this say here? It says this, that total momentum is conserved in the S frame, but not in the S prime frame. So what do we do in physics? We do everything we can to do what? Make sure that conservation of linear momentum is conserved. So this implies here, yes.
Sorry to interrupt. So why in the initial and the final, why does the y component have a gamma denominator while the x component doesn't?
Well, you have to go back to our original explanation of the velocity transformation. And when you go to the original, let me see if I could bring this up to you real quickly. And so when we go all the way back to lecture 1, and you look at the velocity transformation, let me bring this up here. So let me go share my notes. So this is from lecture 1. So when if I go and I share this, what you're seeing here is that when you go and you look at the velocity in the y direction, note that there's a gamma up above. There's a gamma up, when you look at the x direction, note that there's a gamma above and a gamma below. What do? They cancel. But when I look at the y component, there's nothing to cancel out with that gamma. So it exists.
Got it.
Okay?
Okay. That makes sense. Thank you.
No problem. You know, Josh, I should leave a tip jar. So you can thank me that way. Okay. So.
Hey, Carlos.
Yo.
I have another question. Do you mind scrolling up a little bit?
Sure. For which one?
Like a few lines, like maybe 5 lines.
So is it with my lecture notes or the one on my OneNote?
Lecture on the OneNote.
Okay.
Yeah.
Let me get in there.
Yeah. So I was just wondering, because you had said that the Galilean boosts don't transform in space-time, but didn't we kind of do a Galilean boost to get the velocity for ball 1, or the vector velocity for ball 1 is 0b, and then 0 negative b? Didn't we use a Galilean boost to get that? And then we went ahead and tried to get the then we did the Lorentz boost off of what we calculated for the Galilean boost?
Yeah, so, I mean, good question. So one of the things that I'll do here is I'll go back to my lecture notes for lecture 1. And what you're going to see here is that when you look at these boosts here for the velocity, note that if you ignore the denominator, that is the Galilean boost. So they look very, very, very similar, except these guys have denominators. So when I do a Lorentz boost, the difference is that I have to include the denominators. And it's when I include these denominators that you show that when you do a Lorentz boost with momentum, then it really does show that conservation of linear momentum is not conserved.
Gotcha. So you were able to just put in the numbers we solved with the Galilean boost because coincidentally they're the exact same as the numerator in these Lorentz boost equations.
Yes, that's exactly right.
Gotcha. Thank you.
Okay. So one of the things here that if I come back here is that now that we know that that's the case here, that as I said before, we must keep conservation of momentum. At all costs. It's a huge deal. So what we do then is that we then go in, and this tells us that we now must modify the individual definition of momentum. And what we call classical momentum is not going to be the same as the relativistic momentum. And a lot of people are going to say this, well, this is just wrong then. And I'm going to say it's not wrong. Classical momentum, okay, so I'm going to say that this is not wrong, but was designed for V much smaller than C. So when we're looking at relativity situations, we're really looking at very extreme situations. So what you find here is that, we're going to find here is that classical momentum is embedded in relativistic momentum. So it's not that it disappears, it's just that it's now part of a bigger picture. And, you know, it's disappointing that, you know, you'll read, you know, people online that go like, oh, so classical momentum's wrong. No, it's still there. It's just, it's been expanded to a different region of these extreme situations that we encounter here. Now, there's a way to be able to derive this thing. And it turns out that I'm not going to derive it because it doesn't really lead to very much, you know, information. And what you're going to find here is that it really, I mean, it's actually almost not, I don't think it's worth looking at. But so I'm just going to say that without proof, the new modified momentum is given by this guy. So it's given by P relativistic, which is now really just P now. Every time we write P, we should write it this way in the future, even if we're talking about classical situations, but we get lazy, of course. And what we find here is that this guy's going to be gamma times the mass times U. So you could see here that this is the modification. The modification is gamma. And so when I look at this thing, our new relativistic momentum then should be 1 minus beta squared, this guy right here. And that's what the momentum is. So with that, I just want to go in and I want to just start looking and trying to interpret what is going on here. So here I go. So now what I want to do here is that I want to now go and start the interpretation of momentum.
Can you hear me?
Okay, and so here we go. So what you're going to see here is that you may remember this from your physics 4A class. So what we say here is that to write momentum by itself, right? To write this guy like this is meaningless. You write momentum like that, you're full of shit because it has no physical meaning whatsoever. Even though everybody writes it that way, at least know that that's not correct. So what we say here is that the only meaningful thing is changes in momentum. So the only way you can write momentum is a change in momentum. And the way we do that is that we use the impulse momentum theorem to define momentum. And what the impulse momentum theorem says is that it says this here. It says that the change in momentum is caused by the impulse. And this is, of course, what we call the impulse. Okay? It's the change in momentum that this is here. So for the first time, we can actually write down what we mean by objects that approach the speed of light. So what we're saying here is that if I'm going to go plot P versus U. So if you look at this thing here, I have a curve. And I'm going to draw a dashed line right here. And I'm plotting P, which is gamma mu, versus U. So if I'm thinking about momentum, what I'm really saying here is that classical momentum looks like what? Well, if I look at classical momentum, it's this linear thing. Right? So this guy here is what I would describe as classical momentum. So this would be classical momentum. But what you find here is that because of the gamma factor essentially does this thing. It has this asymptote as it approaches U equals to C here. And so the question is, and so in this case here, this would be the so-called relativistic momentum. So the question is, what does it mean here? So what you're seeing here is that a couple of things. The first thing that I would probably point out here is that at low speeds, U much less than C, the momentum of relativistic is approximately equal to the classical momentum. And that's what I mean by the red and the green line being really close to each other. But then you could see that there's a separation right in here. Okay? Why? So now around here, you start to see a separation. God damn it. How do you spell separation? Between the two. And the question is, Why? It's the gamma factor. And what the gamma factor does,
Was this you?
yes,
Then what happened to this?
hold on. I can't right now.
But you have it someplace. Okay.
Okay, and then what ends up happening is that this gamma factor, what ends up happening here is that it changes the difference between these two. So here's what you find here. If I have an object, okay, so imagine that I have a car. So if, right, maybe you have one of these cheesy gold cars, and what you're going to do here is that you're going to go in and you're going to apply a force on this guy. If you apply a force, then the momentum of this car is going to get changed by an impulse. So that means at some point later, this cheesy gold car here is going to have what? A larger momentum. So the question is this here. As I continue to apply an impulse, right? So I'm applying an impulse to change momentum. So as I keep doing this, as U approaches C, then an infinite impulse must be applied. Must be applied to push it to speed C. And since that is clearly, right, this is clearly impossible. And because that's impossible, that means that no object, that is, massive object, can ever reach the speed of light. And that's why no particle can ever reach the speed of light. I know that a lot of times people say that from just special relativity that you can make that statement. You really can't make that statement until you talk about energy or momentum. And momentum gives you the clearest example of what goes on. And let me tell you, the momentum dramatically increases as you get higher up here. And let me just give you two examples. Okay, so I want to give you some examples of just how important you get this scenario here. So let's talk about particle accelerators, since that's what I know best. So if you have a particle accelerator, you're going to see that if you look at, let's just look at the Stanford Linear Accelerator, what you find here is that at the very beginning, you have a little tiny room. I mean, what I mean, a room, we're talking about the size of a small classroom, not very big. And here's where you have what is called the electron gun. So when you shoot this electron from this electron gun here, you literally are taking this electron and it reaches 0.99 C, like within a very, very, very small distance, maybe the size of about a meter or something like that. So inside you have an electron gun, and within a meter, the electron is traveling at 0.99 C. But the accelerator is how long?
Depends.
2 miles long relative to the lab. Jason, shut up. So what you find here is that, so why do you need a 2 mile long accelerator to push this damn little electron? Well, if you go back to the curve, is that it gets harder and harder because the impulse gets larger and larger and larger. And so you need 2 miles to get the speed of this electron at the end to be 0.999996 C. You need that much distance here to apply that impulse and keep increasing the speed of the of that electron here. So, and these guys, this guy never reaches C. It gets
Carlos?
close. Yes.
But isn't it only 3 feet for the electron?
See, that's why I told Jason to shut up. So, Josh, shut up. Yes, I agree. We're talking about our frame of reference, not the electron's frame of reference. Yeah, I know. I agree. I totally agree that that's true. So I should say that, okay, Josh, we're going to draw you here, right? Here we go now. So this is Josh here, and he's now in what? The lab frame. And in the lab frame, it is what? 2 miles long. So now I'm clean, right?
I can
In the
accept
lab
that.
frame. In the lab frame, it's 2 miles long. Dude, nice hair. But the other thing that we could say here is that we can also look at this from the momentum point of view. So it turns out that when you look at accelerators, you have an accelerator. Let's say that this is the accelerator right here. And in the lab frame, I guess I got to be more careful now. It's 2 miles long. What happens is that this beam is now bent around and it's headed towards a detector here. So the way you bend, so I have an electric charge here, an electron that's going to be going in this direction. Now it turns out that the only way to turn electric charged particles is with magnetic fields. So it turns out that what you find here is that you can have a situation where, let's say here, that this is a magnet, and the magnet here has what we call a magnetic field. And what this field does is it actually will take a charge and it will make it bend here. So what you'll see here is that if this thing is moving slow, so if you have a slow moving charge, it turns out that it's easier to bend. Okay? But what ends up happening is that because these electrons are moving with such high momentum, to change their momentum, these magnetic forces of these magnets have to work much harder. So because these have high momentum, it's harder to bend. So particle accelerators that bend electric charges, those magnets are super, super beefy because of the super high momentum of these charges. So So when people are testing the momentum, the relativistic momentum, I mean, this is, like I said before, we're talking trillions of time per hour. This thing is tested again and again and again and again. And as a consequence, if you didn't account for relativity, you would not be able to bend these electrons to go to where you need them to go. So these are two real world applications that they actually, make a huge difference in being able to tell you whether that actually happens or not. So another thing that we should talk about here is that, just keep moving on, I want to say just a couple of more things here. I think I just want to say two things more. And what I want to show you here is that one of the things that I said here is that in the limit, as U is much, much smaller than C of the relativistic momentum, you get the classical definition. Okay, so let's look at this thing here. So if I look at this guy here, that means here that I'm going to look at I'm really looking at beta approaching 0 of the relativistic momentum. And what you find here is that this is the limit of this guy, which is going to give you 1 minus beta squared of mu here. Now note, I can't take that limit. Oh, wait a minute. Yeah, if I take this limit here, as beta gets really, really, really small here, then you could clearly see that I get mu, which means that this is the classical definition. So in other words, it's not that we don't use the classical momentum, it's already embedded in the relativistic momentum. And so you could see that it hasn't gone away. It's just that we were looking, the redefinition gives us a much more complicated scenario here. Now, this is the last thing I want to say about momentum before I go on to energy. And this is what I want you to think about here. Some physicists, okay, and I'm going to say that these guys really piss me off. They piss off a lot of people, by the way. Some physicists think to write that the relativistic momentum is really this. What they do here is that they come in and they go like, oh, this is gamma mu, and then they separate this thing like this. And then they come in and they go, you see, this is just like regular classical momentum. And they call this the relativistic mass. And they say, oh, that's how you define it. So what this does here is that this implies here that this relativistic mass is then this gamma factor times m. And what they do here is they actually come in and they put this knot right there. And what this tells you here is that this is what they call the rest mass. And then they say that this gamma factor does this. So this is what they say here. And so I really want to comment on this thing here. Okay? Because if you read anything in the newspaper, anything in layman's books, what they'll claim here is that, what they say here is that objects that approach, or excuse me, how do they say that? They say it this way, that moving objects are more massive than stationary objects. Right? As an object moves, its mass varies. Well, I have a lot of problems with this. Okay? There are numerous problems. The first problem here, mass is a Lorentz invariant. And what I mean by that is that when you look, remember how we write down invariants, we got to do the dot product. So what you're going to see here is that we're going to get an equation for the mass that's mass squared. Why? Because that's how we deal with scalars in space-time. And what you find here is that you're going to see that it's a combination of the energy minus the momentum squared like this. So this is measured from the S frame. And then what you're going to see here is that if I move into the S prime frame, that all observers are going to measure the mass to be the same. So this implies here is that all inertial observers measure the same mass. Now, note that that's a technical thing, and we'll hit this a little bit later, how you can actually do that. But just built into relativity is this condition right here. And that tells us that regardless in which frame you're in, the mass is always, always the same. But there's many other huge problems. Okay? So if one defines that M relativistic is gamma M, then you must throw away almost all of the foundations of physics. Okay? If you use that mass, there's a problem here, because look, if people say like, oh, so what they'll say here is that all we need to do, this is what they say, is to replace M classical with M relativistic. That's what people say here. So let me show you here. So if I start with classical force and I write M classical and I write it like this, and then you go, oh, so if I want to look at the relativistic one, then all I have to do then is then add it like this here, right? That would give you that impression here. Well, guess what? It turns out that if you do this thing, you know what happens? They're not the same. But wait a minute. If the force is not the same, then when I look at the momentum, what happens to the momentum? That's not the same. What happens to the work energy theorem? Over this, guess what? That's not the same. And so therefore, you have to change the definition of all the energies, all the momentums. Man, you're just screwing with everything. And by the way, the same thing goes with the angular momentum, right? Because now all of a sudden, if you go and you go like this, oops, when you're looking at the dt, that's not the same. So you change the whole foundations of physics. So why do people use the rest, the relativistic mass? I think it's laziness. I literally think it's laziness. It's not appropriate to think about the mass getting heavier. And by the way, in space-time, you can explain why you have length contraction. You can explain why you have time dilation without any problems using the light clock. But when you accelerate a mass with an impulse, you're going to find out that there's no way to physically explain why a particle gets heavier as it gets faster and faster and faster. So it's a bad idea to actually do that, but people do that a lot. So let's go to the next piece here. Once I hit this piece here, now we could then start talking about examples here. So now the last piece I want to do before we start going after examples is relativistic energy. We expected that we would have to modify momentum. And we also expected that we would have to modify energy because of the Lorentz boost here. And so what we've got to do here is that the question that we've been asking is, how is energy modified in order to preserve conservation of energy? Right? How am I going to modify to conserve conservation of energy? So it turns out that the two broadest, that doesn't look right. How do you spell broadest? I think it's something like this. Forms of energy are kinetic energy and potential energy. So I have to address both of these. So let's start off with kinetic energy first. Like, as I've said before, kinetic energy, just like I said with momentum, so if I write kinetic energy as 1/2 mv squared like this is meaningless, right? It has no physical basis whatsoever. So what is meaningful? We have to use the work energy theorem to define kinetic energy. So in other words, if I do work, then this must be the force along some direction, and then this will be my change in kinetic energy. This definition is meaningful. So the thing about this is that if I want to talk about relativistic energy, then what I need to do here is that I have to bring in momentum. So what's the correct way to write down Newton's second law? So if you look at Newton's second law, you should only write Newton's second law in one way. And that essentially says what? That the force is equal to the rate of change of the momentum. And when I look at the rate of change of momentum, we've already defined momentum now. And we already know that momentum here is going to be gamma mu. So I got to take the derivative of this guy with respect to time here. So what I want to do here is that this thing here, this is good, right? That's the way, that's what the principle of relativity tells me. The laws of physics are the same for all inertial observers. So this is a valid statement for all frames of reference. So the question is, how do I modify this in terms of relativity? So what I'm going to do here is that I'm going to take my force here and I'm going to plug it right into there. Now it turns out that the algebra here is super, super tricky. And if you go to my notes, I'll let you go through those details, but it's not trivial. And so what you're going to find here is that I'm going to say now, if I do that, I got to combine both of these, then the work is then going to be what? Well, mass, remember what I said here, mass, what's mass here? Mass is what? This is an invariant. It does not depend on time or velocity. So what am I going to do with that mass? I'm going to bring it outside the integral because it's an invariant for all frames of reference. And so then you're going to see that I'm going to get d of gamma u. Then I'm going to get dt. And if I move in one dimension, then the dot product goes away. So what you're going to find here is that I can kind of clean this up a little bit. And the way I'll clean this up is that I'm going to make a change in variable. So what I'm going to do here is that now I'm going to do a change in integration variable. I'm going to go from x to u, okay? And if I go from x to u, what you're going to find here is that I could now come in and I could redefine the work so that it's m of d gamma u dt dx, and this change in variable then gives you this expression here. You're going to get an integral that goes from 0 to u of u du of gamma u here. So essentially, I just use a change. There's lots of ways that you can do this. You can think of this as using a chain rule to go from here to there, or you can write down a Jacobian to do a change of variable, because you're really changing coordinate system from position into velocity. But then this guy right here is a monster here, okay? This guy right here, this is not easy to write out. And then I'm going to let you go into my lecture notes if you want to know the details. But when the dust settles here and you calculate this whole integral, which is, by the way, it's many lines, by the way. The algebra is intense. Here's what you find. You get this result right here. You get the change in kinetic energy. And this change in kinetic energy reads like this. It reads gamma mc squared minus mc squared. So remember, there's numerous missing steps. And I don't think that it's really beneficial to the physics to actually go in and derive it. Okay, like I'm not afraid of it, and you could find it in my notes here. But this is the kinetic energy right here. This is, maybe I should call this is the relativistic kinetic energy. And so what I want to do here is that I want to take this and I want to start to interpret this thing. Okay? So if I start to interpret this thing, I then go here. So I want to interpret this relativistic kinetic energy. And what we find here is that, as expected, it's the change in the kinetic energy that's important. And what you're seeing here is that the interpretation of this thing here is that you note that there are two terms to the kinetic energy, right? There are two energy terms. So when you look at this thing here, what you're seeing here is that I'm getting a term that reads, right? I'm getting gamma mc squared, and I get mc squared. And what you're seeing here is that there's a term here that, note that, does not depend on speed. And because it doesn't depend on speed, what we say here is that this must be the rest energy, right? Because in this case here, u is equal to 0 here. And what we say here is that this is after a long time here. What people do here is that they come and they interpret this rest energy. And what we say here is that this expression, mc squared, is considered to be a form of potential energy. Of an object. It's sort of like it's, if I could say this, it's its own energy. It's its own energy of being, I guess. That's a good expression. It's its own energy of being. And so this is so common that people typically write it like this. So when you see this E naught in relativity, they mean the rest energy here. And what you're finding here is that, again, I can look at energy or momentum to describe whether I could accelerate a particle, to the speed of light or not, but I still have to go back and hit the second term. So if this is really the case here, I'm going to write this down very, very, very loosely here. You could imagine then something like this here, that what is this term right here? Well, I could write something down wrong that will get to the point really quickly, or I could use this information of thinking of this as potential energy here. So the correct way to look at this thing, so to interpret what is gamma mc squared, we look at the total energy. And so when I think about the total energy, we typically think of this as being what? The kinetic energy plus the potential energy. okay? But remember, it is meaningless to talk about energy at one point. So I'm really talking about what? Changes in energy. And so if I do that, then you could imagine that if I write the kinetic energy of this system, it's going to be gamma mc squared minus mc squared plus the potential of an object, but we already said that the potential here is this guy right here, this energy of being, and you could see that this term right here and that term right there cancel each other out, so therefore we can write the total energy by this expression right here.
Does this we relate to that E equals MC squared from because I learned that like a long time ago, and I don't know if that's
Yeah, well, we'll see if what you learned a long time ago is the same thing that we're actually talking about right now. Because this is one of these concepts that gets thrown around like crazy. But let's move on here for just a little bit longer. But I'll come back and I'll deal with the word E equals mc squared. Because it's misused a shitload. And there's a lot of misconceptions about it. And I want to make sure that you walk out of this course going like, okay, like everybody writes, right? They write this term right here. Well, is that a change in energy? If I write this, do you see anywhere where I say change of energy? Look what I said here. If you write kinetic energy as 1/2 mv squared, that's a bunch of bullshit. That's meaningless, right? If I come over here to the momentum and I tell you that the momentum up here, if you write momentum as gamma mu, that's meaningless. So if you write E equals mc squared, what the hell does that mean? That means nothing. It's a meaningless statement. So the question is, we have to go in and talk about what do I mean by E equals mc squared? And we're not there yet. But what I do want to show here is that now, let's look at the same type of example that we looked at before here. And the question is, why can't we accelerate an object to the speed of light? Well, if we go back to our previous situation where we had a car that we were trying to accelerate to the speed of light. And what we're going to do here is that this time, when we apply our force on our cheesy gold car here, what you're finding here is that we agree that the speed of this car is getting faster and faster as we're doing it. But this time, what are we doing it over? We're doing it over some distance delta x here. So if I do work on this car, right? So what we're doing here is that we're applying work to speed up this car. Well, if I do that, what do I see here? So what I'm going to do here, there's lots of ways to plot this. The way that I seem to like it the best is that I'm going to plot beta versus the relativistic kinetic energy here. So if I plot beta versus the relativistic kinetic energy, you're really plotting this relative to gamma. So if you're plotting this relative to gamma, when V is equal to C, then what we find here is that beta is equal to 1. So if I look at this thing here, then that means I have this line, or that's the speed of light. So I'm really plotting beta versus gamma. And when you look at the curve, this is what you're going to see the curve do. It's going to go like what? What you're going to see here is that this curve right here is essentially plotting this thing here where it asymptotes at beta equal to 1.